Okay guys, today is lesson 8. I can use the value of a ratio to solve ratio problems in a real world context. I can use the value of a ratio to determine whether two ratios are equivalent. So how we've determined if two ratios are equivalent in the past is by drawing a tape diagram or doing that little V shape to prove that they have the same C factor. We're going to today be building on our knowledge of value and how we use fraction form to represent value. And we're going to be using that to determine if two ratios are equivalent today. Where it says the value of a ratio, that means we're not only going to be writing the ratio in fraction form, but getting it down to its absolute simplest form. Okay, so we're going to be doing some reducing of fractions today. Let's get started. One important thing that we need to kind of train our brain to remember is factors. So when we're reducing fractions, we are looking for factors in both the numerator and the denominator that are similar, so that we can reduce by that factor. For example, if the numerator and denominator both share a factor, so if I had 14 and 20 in my fraction, I see that they both share the number 2. That is their highest factor they have in common, so I can reduce both 14 and 20 by 2. So we'll get more into that. I just want you to kind of remember how we use factors. You think about any number that can be a factor of that. For example, 14 has factors of 1, 2, 7, and 4. So you want to look for factors that both numbers have. All right, so I'm on exercise 1, and the top part is just a little bit of a review. It says circle any equivalent ratios from the list below. So we're just going to do this a way that we've learned in the past. So I can take 1 to 2 and 5 to 10. And I'm going to show that they have, if they're equivalent, that means that they both share a C value. So 1 times something is 5. Well, I know 1 times 5 is 5. So 2 times 5 should equal 10. And yes, that is true. So these two ratios are in fact equivalent. So I can circle those two together. Okay, now I'm going to take a look at my second pair, which is 6 to 16 and 12 to 32. And let's see if they share a C value. 6 times what is 12? 6 times 2 is 12. Okay, and so if they are equivalent, I should be able to plug 2 into here as well, and it would still be true. Is 16 times 2 32? Yes, it is. So these are also equivalent. These are not equivalent to each other because they do not share a, you can't have 5 to 10 and 6 to 16, okay, because 5 times nothing is 6. Okay, so that's not going to work. Those are not equivalent. Just these two and then these two here as well. Okay, so for this bottom part here, I'm going to refer back to the idea that when it says it wants a value, it wants its simplest fraction form. For example, even though the ratio might be 4 to 2, I could reduce that down to 2 over 1. So I'm going to talk about that down here and model it a little bit. But this is really where you want to know your factors. All right, so it says find the value of the following ratios, leaving your answer as a fraction, but rewrite the fraction using the largest possible unit. Largest possible unit means like in fractions, the number on the bottom is going to be smaller, like 1/2 is a larger unit than 1/4. Okay, so that's what it means. Reduce it to its simplest form. All right, so we have here the same ratios that we used from the part A, so, or the top portion here. Okay, so for 1 over 2, I cannot reduce that down anymore. That is already and let me zoom in a little bit. That is already in its simplest form. It doesn't reduce down any further. So that one, the value of the ratio is 1 over 2. But now here where I have 5 over 10, that does reduce down. Okay, because I can look at these two numbers and they do share a factor. I know 5 goes into 5 and 5 goes into 10. So what I'm going to do is I'm going to divide both sides by the same number. So 5 divided by 5 is 1. 10 divided by 5 is 2. Okay, so that is down to its simplest form. That is its value. Okay, now when I go down here, and I don't want these to blend together, so I'll pick a different color. 6 over 16. Okay, again, I can tell that that's going to reduce down because I know that, for example, they both can be divided by 2. They're both even numbers. So I'm going to divide both sides by 2. 2 over 2. Okay, 6 divided by 2 is 3. 16 divided by 2 is 8. So its value is 3 over 8. And then this bottom one here, 12 over 32. I know that can reduce down. Okay, they both share a factor of 2. They both share a factor of 4. Okay, so I'm going to divide both sides by 4, or else I'm just going to have to reduce down again. So I want to try to find the largest factor they have in common. So 12 divided by 4 is 3, and 32 divided by 4 is 8. Okay, and this bottom part here, it says, what do you notice about the value of equivalent ratios? So like we said on the top, that 1 to 2 and 5 to 10 are equivalent ratios. And if you notice, they have the same value. The value is the same on these two ratios that are equivalent. These two as well, these equivalent ratios, they have also the same value. So one thing we're noticing is that if ratios are equivalent, they have the same value. A note on the bottom that's important to notice, 1 to 2 is not the same ratio as 5 to 10. So we don't say they are equal. The ratios are not the same, but their values are equal. Example 2, we will try this together. Here is a theorem. If two ratios are equivalent, then they have the same value. And that's what happened in our last problem. We had two ratios that were equivalent. They did have the same value. So is that always true? Can you find any counterexamples to the theorem above? So let's just pick, I'm going to pick ratio 2 to 3. And I'm going to find an equivalent ratio. Okay, so let's do just 3 as the C factor here. 2 times 3 is 6. Need to do the same C value. 3 times 3 is 9. Okay, so 6 to 9 would be equivalent. Now let's see if they share a value. They have the same value. So 2 to 3 can't reduce down any farther. There's nothing that no factor that they both share. So 2 to 3, that's just as low as it gets. That's the value. 6 to 9, can I reduce that down? Yes. They both share a factor of 3. So I could divide both sides by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. There's the value. And oh, they are the same value. So here's another example that it's true. So we were not able to come up with a counterexample. And if you feel like it, you can definitely try your own and see if you can come up with one. But I tried several to practice and I could not come up with one. So cannot disprove this theorem. It is a true theorem. If two ratios are equivalent, then they have the same value.